Okay, so oxidation reduction is basically, we've talked about this before, redox reactions. It's where electrons are transferred from one reactant to another. And in this class, we'll have one metal on one side, and then we're going to have it convert into something else. And so if you guys want to write this acronym down, easy way to remember oxidation reduction, oil rig, oxidation is loss, reduction is gain. And we're talking about electrons here, okay? So if if an element gains electrons, it is being reduced. And if it is losing electrons, it is being oxidized, okay? So make sure you guys keep oil rig in mind. There will for sure be oxidation reduction on the AP test, whether it has to do with solutions or whether it has to do with electrochemistry. So just make sure you guys remember what oxidation reduction is. Okay, so I'll give you guys a second to copy that down. Okay, so we got an example of a redox reaction right here. If you guys notice, calcium has a charge of 0. It's in a solid form, which means that its oxidation number is 0, okay? Oxygen usually is going to have a, this is in its gaseous form, the natural state, so this is also going to be 0. So calcium and oxygen both have an oxidation number of 0. Now remember, oxidation numbers have to do with the charge sometimes, but it's not always dependent on the charge, okay? But these guys are both 0. And if you notice, as we go to calcium oxide, when we go to a compound, oxygen is going to have an oxidation number of -2. That's one thing you just want to remember. Oxygen, when it's in a compound, 99% of the time it's going to have a charge of -2. There is one exception, it's peroxide, and that's when it's O2 2-. Then it'll have a charge of -1, but 99% of the time it will be -2. And so since this is balanced out, calcium will be +2. So calcium is going from an oxidation number of 0 to +2. So if it goes from 0 to +2, is it being oxidized or reduced? Yeah, it's being oxidized because it is losing electrons, right? Remember, oil rig, oxidation is loss. Calcium is going from 0 to 2, so it is losing electrons. And that means that oxygen is going to be reduced. It is gaining electrons. That's why you go 0 to -2. It's a little bit confusing because if you gain electrons, you become more negative, and minus we associate with losing. But in this situation, you're gaining electrons, so you're getting more negative. Okay. All right. Any questions about that? Hopefully, this rings a bell. We did this a long time ago, so it's okay if it doesn't, but we'll do some practice problems. Okay, let's move on. I'm not going to go over how to find the oxidation numbers. This is the same rules that we had in Unit 4, so I'm going to skip it, but I have it here if you guys do need to review it. But let's see if you guys can try this out on your own. So I'll give you guys about a minute. See if you guys can do 14.1, and if you feel comfortable, you can also try 14.2. So in 14.1, we are trying to determine the oxidation state of every element in sulfuric acid, okay? So if you guys need to know or check out the rules from the top, you guys can do that. But the hint that I'll give you is, remember, oxygen, when it's not in this pure elemental form, it is 99% of the time going to be -2. Okay, so use that as a hint. Try to figure out the oxidation numbers for every element in H2SO4. Alrighty, guys, let's go over the oxidation numbers. So this part is still review. So if you guys take a look at oxygen, we said that oxygen is going to have a charge of -2 most of the time, or oxidation number of -2. So if we have 4 of them, what is the total oxidation number of all 4 oxygens? Yeah, -8, right? -2 times 4, so it's going to be -8. Okay, now this compound is neutral, it's balanced out, and so that means everything here needs to end up at 0 when you combine the numbers. Now, hydrogen is the other one that we can typically find the oxidation number for. Hydrogen is bonded to some nonmetals, right? And so what's the oxidation number on hydrogen when it's bonded to nonmetals? Yeah, +1. And if there's 2 of them, that's going to be +2. Okay, so the two rules that we kind of implemented here is that oxygen has a oxidation number that is equal to -2 99% of the time. Hydrogen has an oxidation number that's equal to +1 when it's bonded to a non-metal. When hydrogen is bonded to a metal, it's +1 or -1. So hydrogen's kind of fake, depending on who it's with, but these are non-metals, and so hydrogen is +1, okay? All right, and then we said the sum of these have to end up to 0. The sum has to be 0. And so what does sulfur need to be in order to get this to 0? Yeah, +6. Okay, so there you go. Hydrogen is +1. Sulfur is +6. And oxygen is -2. There you go. Any questions about that? All right, so I'm gonna give you guys another minute to try out 14.2. I want you to figure out here which element is being oxidized and which element is being reduced. I'm gonna use the same rules that we did before. So try it out and then we'll go over it in just a second. Alrighty guys, let's go over the 14.2. Okay, so if you guys take a look at magnesium, let's start on the left side. What is the oxidation number for magnesium? Yeah, this is gonna be 0. And the reason why magnesium is 0 is because it's in its pure elemental form. And so when a metal is by itself, it's going to have an oxidation number of 0, okay? All right, let's move on to the next one, hydrogen. Okay, what's the oxidation number of hydrogen when it's bonded to a nonmetal? Yeah, +1, good. And then chlorine is going to obviously be -1. And that's another trick you can remember. The halogens, the guys on the second to last column, they're gonna be -1. Okay, let's move on to the right side. Okay, so if you look at, let's start with the easy one, hydrogen. If you look at hydrogen, what is the new oxidation number of hydrogen on the product side? Yeah, 0, because hydrogen's pure elemental form is going to be H2, hydrogen gas. And so if you guys notice, we have a change in the oxidation numbers, right? Hydrogen goes from 1 to 0. So did it gain or did it lose electrons? Yeah, this guy gained electrons. He made gains, right? Gained electrons. So if you gain electrons, was it oxidized or reduced? Yeah, so hydrogen was reduced. All right, let's move on to the next one. If we take a look at magnesium, what is the oxidation number of magnesium on the product side? Yeah, this is +2. So if you guys take a look at it, there was a change. It went from 0 to 2. So did it gain or lose electrons? Yeah, it lost electrons. Okay, which means that obviously it was oxidized. And then if you want to finish the math, chlorine stayed -1, so chlorine stayed the same. Okay, so the species that was oxidized was magnesium. The species that was reduced was hydrogen. Just make sure you guys are really comfortable with this because as we go on to the more complicated stuff, you're just gonna have to be able to identify this quickly. If not, you won't be able to do the stoichiometry and stuff that comes with this, okay? All right, any questions? All right, let us move on then. So oxidation and reduction go hand in hand. Basically, if there's oxidation, there always is gonna be something being reduced, which makes sense because the electrons have to move somewhere, right? And so when we have a reaction, so we have a reaction like this, just to do this really quickly, you should be able to see that iron is going to be oxidized because here you start, actually, I'll write oxidized. Iron starts off as 0 and then it ends up as +2. And then if you guys look here, hydrogen becomes reduced because hydrogen started off as +1 and then it goes to 0. Okay, and so when you have a balanced equation like this, you can write something called a half reaction, okay? Half reactions are where you split up what's going on inside of the full reaction into what's being oxidized and reduced. So the only thing being oxidized is iron, right? So if we're gonna write the half reaction for iron, we just need to include what's happening to iron, Okay, so iron, we said, is losing electrons. So what's happening in the half reactions, we write Fe, draw an arrow, and we show that it becomes Fe2 plus, and it's losing 2 electrons. These guys broke up. Okay, so that's what's happened. Well, that's how we write a half reaction. Okay, and if you have something that involves oxidation reduction in your FRQ, just make sure you're ready to write a half reaction, because they will be asking for that more often than not when there's oxidation reduction in an FRQ. Okay. So all you need to do when you write a half reaction is just take out what's being oxidized and just kind of simplify what's happening to that guy. And then obviously the half reaction for reduction is the same thing. Hydrogen was reduced. So we start off on the left side with some electrons, right? They were split up and then they get together. Okay. And so that's how you write an oxidation reduction half reaction. Now, if you guys notice, there are free electrons on both of them, right? And the position of them depends on if it's oxidation or reduction. If it's oxidation, the free electrons are on the product side. And if it's a reduction half reaction, the electrons are on the reactant side. Okay, so just keep that in mind. Any questions about that? Easy peasy? All right, let's see if it's easy peasy. Let's move on. Okay, so for 14.3, what I want you guys to do is same thing as before, identify the species being oxidized, reduced. And then this time, once you're done with that, I want you to write the half reactions as well. So take about, I'll give you guys like 2 minutes to do that. Alrighty, guys, let's start going over this. So hopefully this wasn't too bad. You should have noticed that chromium was oxidized. That's why it went from +1 to +3, because it lost some electrons. It got less negative. And then that means that tin was being reduced. Okay, so your species that was being oxidized was chromium, and the species that was being reduced is tin. Okay, all right, let's write the half reaction. So I'm going to do the oxidation half reaction first. For the oxidation half reaction, we're going to start with chromium. Okay, and then it's going to break down into chromium 3+, and it's going to have 2 free electrons. It's releasing 2 electrons. So it was +1, and to get to +3, it needs to get rid of 2 electrons. Okay, reduction is going to be for tin. Now, if chromium has free electrons on the product side, that means we're going to have the same number of free electrons on the reactant side. So the electrons that chromium gives up, tin is going to eat them up, and it's going to turn into 2+. Okay. So again, an easy way to write the half reactions is remember oxidation. The electrons are on the right side because it gives it up, it breaks up, and then in reduction they get together. So the electrons are on the left side. Okay. All right, any questions? Hopefully that's not too bad, because we're going to have to get a bit more comfortable with these. Okay, let's move on. So we did acid-base titration, but now we're going to have redox titration, okay? So we know that titration is a slow addition of a solution at a known concentration to another solution of an unknown concentration. So if you guys remember, we did titration a long time ago, and we talked about it in the acid-base unit, but we're basically just dropping a solution that we know the molarity of, let's say it's 2 molarity, and then we're dropping it into a solution that we don't know the molarity of. That's what titration is. And then depending on how much you add, that tells us the concentration of the one below. That's titration in a nutshell. Okay, so titrations are used in acid-base, but we can also use redox with titration. Okay, so what I want you guys to do right now is take a look at 14.4. And what I want you to do is just very quickly just sketch out what is going on. That'll kind of help us understand what's going on in this situation. Okay, I want you to read the problem, and I want you to sketch out what is happening. Okay, guys, let's kind of go over what the sketch is. So it's telling us that we have 50 milliliters of sodium oxalate in an Erlenmeyer flask. So if I did kind of a very simple drawing, okay, this is my Erlenmeyer flask. And inside of the flask, we got 50 milliliters of sodium oxalate. So Na2C2O4. So sodium oxalate is on the bottom. Okay. And then we have a acidified solution of potassium permanganate. So I'm going to be dropping potassium permanganate because it's being titrated. The concentration is 0.135 molarity of potassium permanganate. And basically, we are adding this to that. We're dropping potassium manganate, okay? And then it tells us that we are adding a total of 14.56 milliliters of potassium permanganate. And so what we are looking for is the concentration of sodium oxalate, okay? So this is the scenario that we're given. Okay, so hopefully that makes sense, what is actually going on. And then it's asking us, what is the concentration of the oxalate solution? Okay. Now, if you guys notice, this is a little bit weird because normally you have a full chemical reaction that's given to you, right? But here you're given two half reactions. So in order to calculate the molarity of sodium oxalate, you need to combine the half reactions to write the full reaction. Okay, so we're going kind of in reverse now. In the previous examples, we were splitting up the reaction into the half reactions. Now we're taking the half reactions and turning them into a regular reaction. Does that make sense? Okay, so let's try that. I'm going to get rid of the picture just so we have a little bit more space. But what we're going to do here is step number one is going to be writing the full reaction. Okay, that's step number one. We're going to write the full reaction. But the qualifier I want to give it is that it needs to be balanced, okay? Because all chemical equations need to be balanced. So you might think, hey, we can just kind of put everything that's on the reactant side on one side and everything that's on the product side on another side, right? But if you guys take a look at these two half reactions, anyone identify what the problem is? What was that? It's not that it's reversed. Anybody noticed? The key thing is it needs to be balanced. Yeah. What was that? It's not two reductions. It's still one compound being reduced. Yes, the electrons. If you guys noticed, I know it's very like hard to see, right? But how many electrons are on the reactant side? There's 5. And then how many are on the product side? 2. So remember, we said that if we're going to combine the reactions, they need to be balanced, right? And so what we need to do is we need to make sure there's the same number of electrons on the reactant and the product side. Okay, so we need to find, you guys might not like this term, but the most, what is it? The least, what's that called?
Common denominator.
Not denominator.
Common factor.
Factor, thank you. Most common factor, or the lowest.
The kids know it as finding the common denominator.
The thingy that they turn into together. Okay, yeah, the thingy they both turn in together. Yeah, so what we need to do is we need to turn both the electrons into 10, right? Because that's the closest. Is it multiple? Lowest common multiple?
Lowest factor.
Factor?
I think factor.
Lowest product.
Product, yeah, lowest product. You know what, whatever. I'm not good at
But
math.
product, I mean, it gets confusing in chemistry, but the answer to multiplication is a product.
You
So
are
we call it
correct.
factoring,
Factoring.
but you're not finding the lowest. Yeah, you're not finding the lowest common factor.
I'm letting down my Asian ancestors by being bad at math. I'm sorry. I'm
But the
sorry,
lowest factor would be
ancestors.
2 and 5.
But you know what? I don't even know my grandpa's name. So, all right, let's get the whatever, the factoring or whatever Mr. Pepik said. So
Did you know I don't know my grandfather's name either?
really? Oh,
I know one of my grandfather's names.
I don't know either of them. I know their last. I know their last name.
Well, because you have to know.
I know one of their last names.
Thurston was my mom's dad's name. But I don't know.
Thurston?
Thurston.
That's a sick name. But
That's
if
old
you
school.
but that would be a bullied name nowadays.
Yep.
All right, anyway, so if we're going to get the reduction half reaction to 10 electrons, what do we need to multiply everything else by? 2, yeah, because this was times 2. So if we rewrite this half reaction, we would have 16 protons, 2 permanganates. Well, I might run out of room. Got 10 electrons. You got to multiply the manganese ions, and you're going to have 8 waters. Okay. So that is the half reaction for, or that is the balanced reduction half reaction. Dang, dude. Whoever named these, a lot of words. Okay, on the oxidation side, what do we need to multiply everything by? 5. Okay, so we got 5 whatever the name is, that thing. And then you gotta multiply this by 5, and that's 10 carbon dioxides. Sorry, this looks like an S. That's bothering me. 5. Beautiful. Okay, now we can put them together. Okay, so if we combine these 2 half reactions, what we're gonna do is we're just gonna copy down what's on the left side, put them together, copy down what's on the right side, put them together. So if we combine them, we'll get a very, very long reaction. 16H plus 2 permanganates plus 10 electrons plus 5 chromates. Draw an arrow. Got 2 manganese ions. Got 8 waters. Plus 10 CO2 plus 10 electrons. Holy moly, that's a fat reaction. All right. I'll let you guys finish copying that down because that is probably the longest chemical reaction we've written so far. Now do you guys know why I hate this unit? There's so much writing. I have little fragile hands. I can't write this much. Okay. Now, before we start using this for our stoichiometry, we need to get rid of the common factors. So what do we have on both the product and the reactant side? E, yeah, we got electrons. So what we can do is get rid of the electrons because remember Hess's law, they cancel out with one another. So we can get rid of the electrons. So this is a little bit more manageable. And there you go. We got our, does anyone remember what this is called? It's a long time ago. It's the net ionic equation. Yeah, net ionic equation. Okay. So that's what we get with the full reaction, and we balance it too. Okay, let's move on to step 2. The second thing that we're going to do is we're going to use the stoichiometry. So step 2 is our stoich to figure out, what is it? How many moles were added? Okay, God bless you. Okay, because that's what titration is. We're just trying to figure out how adding one compound is going to affect the other one. So we're going to find the moles added. Okay, so if we take a look at it, we said that we added potassium permanganate. Okay, so we're adding permanganate. So out of these three, 1, 2, and 3, which of these ions were added? 1, 2, or 3? Which one was added? If potassium permanganate was added. Potassium permanganate is KMnO4. Yeah, so 2 was the one that's added. Do you guys see that? We added potassium permanganate. KMnO4 in solution breaks down into K and MnO4 minus, which means that we're adding MnO4. Does that make sense? Okay, so what that means is, since it's a 1-to-1 ratio, if I added 14.56 milliliters of manganate, and the molarity is 0.135 molarity, what we can do is we can use the molarity formula to find how many moles were added, right? Okay, so I'm going to give you guys about a minute to do that. Okay, the moles added is molarity times liter. So take about a minute to calculate how many moles of manganate we added. Okay. I'll close the door because it smells like gas. Alrighty, guys. So for the moles added, we just need to multiply the molarity times the volume, but it needs to be in liters. So we're going to move the decimal 3 times to the left. So for your calculations, you would have done 0.135 times 0.01456. I'm running out of space. Okay. And that gave me, and you guys can correct me if I'm wrong, because I'm usually wrong, but I got 0.00197 moles. Everyone got that? Okay, so we calculated how many moles were added. So we added 0.00197 moles of manganate. Okay, however, the problem is not asking us to find the moles added. What we're looking for is the concentration of the oxalate, right? And oxalate is going to be this right here, CrO4 minus. So what we can do is we can just set up one conversion factor and look at our balanced equation. Okay, we want to find oxalate, so I'm going to put moles of oxalate on the top, and I want to get rid of permanganate, so I'm going to put moles of permanganate on the bottom. Okay, so what's the ratio between oxalate and permanganate? 5. Yeah, 5-2. 5 oxalates per 2 manganate, so it's 5/2. And so when we use that conversion factor, that will give you the moles of oxalate that were in the original flask. Okay, and I'll do the conversion for you. It's very easy. Times 5 divided by 2. And you should get 0.00493 moles of oxalate. But we're still not done. Isn't this horrible, guys?
It's fun.
Do you like this class?
Yes.
My gosh, I'm not doing my job correctly then. I'm goofing somewhere. Okay. So we got the moles of oxalate. Anyone want to take a shot at why we're not done yet? Yeah, molarity. We're trying to find the concentration. And so all we need to do now is divide this by 50 milliliters, and then we'll be all done. I'll give you the final answer, but you guys should be able to figure it out. All you got to do is divide this by, oh, hold up. That's not right because of the conversion factor. Thank you, guys. So we do need to convert it. And then how many moles of oxalate per sodium oxalate? Or actually, no, it's still 1-to-1
No.
because sodium has a constant double.
Volume.
Wow, you guys are smarter than me. Wait, no, because you're not gonna combine the volume because this is the moles that was in there in the original volume. We're looking for the original concentration, not the new concentration. Because the new concentration is 0 because it's completely neutralized. Haha, thought you guys are smarter than me, huh? Thought you got me there. Usually you guys are smarter than me, but not today. Mr. O prevails today. Okay, so yeah, molarity of the original concentration is going to be 0.00495 moles of the oxalate divided by 50 milliliters, which is 0.05 liters. And that's going to give us a final concentration of 0.0986 molarity. And this is technically going to be for your oxalate, the C2O4 2-. But if you guys notice, there's only 1 mole of that inside of sodium oxalate, so we can keep the same answer. Now, if we're looking for sodium, we would have to double that because there's 2 sodiums per sodium oxalate. But since we're just looking for oxalate, we can just keep it the 1-to-1. Okay. And now we are finally done. So this thing up here at the top right is going to be our final answer. And again, just to clarify, we're not adding the volumes because we're looking for the original oxalate concentration, not the total new final volume. Okay. And that wouldn't even work because it's neutralized, so we wouldn't have that. Horrible question. Evil. You know something's wrong when they make you write your own chemical equation. It's just be given to me. All right. Any questions? Okay. Okay. Let us move on then. Okay, so this is the second half of electrochemistry. The first half is about redox, where the electrons move around and whatnot. And the second part is about something called reduction potentials. And reduction potentials are where we look at the actual electric potential or voltage that has to do with every half reaction. Okay. So basically the point of this is that every single half reaction has some type of electric potential. Electric potential is basically the energy that's produced by the electrons moving. Okay, so do the electrons want to move a certain direction? And if they move that direction, how much energy are they going to produce while moving that way? Okay, so we got some examples right here. This is the reduction potential for zinc ion. So zinc ion is going to gain 2 electrons to turn into solid zinc. And this is going to be this is the notation for the reduction potential. Okay, pretty easy, right? Just same thing that we did with like Hess's, not Hess's, like enthalpy and stuff like it's just something we add to the end of the reaction. Okay, now same thing as normal stoich. If you flip the equation, you're just going to multiply or change the sign for the reduction potential. Okay, so the reduction potential from the first reaction going from zinc ion to solid zinc was negative 0.76. But if we go the other way, where we go from solid zinc to zinc ion, it's positive 0.76. Okay. Okay, so those are kind of the rules that you want to write down. Okay, when you flip it, you flip the sign. All right, so far so good? Okay. Now, this is the key thing that you guys want to write down, and this is what you really want to know for reduction potentials, because this will be the guiding factor for the rest of the unit. Okay, so the larger the reduction potential for half reaction, the more likely it is to occur. So the half reaction that is most likely to occur is the one that has a larger reduction potential. So the bigger the number of the reduction potential, the more likely it is to happen. Okay, so F2, just kind of as an example, has a very, very large reduction potential, plus 2.87. So this reaction is more likely to happen. Okay, so if we compare it to the previous example right here where we had zinc, zinc only has a reduction potential of 0.76, and this has a reduction potential of 2.87. So the F2 half reaction is more likely to happen. Okay. And then we have another example underneath. Solid lithium has a super large oxidation potential, which means this is really going to want to happen, plus 3.05. Okay. And then we got some other rules right here. Not super important, but kind of helps us when we're calculating the potential. If you add the potential for a half reaction to potential of a reduction half reaction, basically, if you want to find it for a full reaction, just add the oxidation and reduction potentials together. Okay, and you don't want to multiply the potential by the coefficient. We just kind of leave it as is. Okay, so why are we talking about this? So there's a very common scenario that you'll look at for an oxidation or for reduction potentials. And since I'm a great artist, I'm going to draw it out for you guys, okay? So prepare to be amazed. And I would recommend kind of drawing this out too. Okay, so what happens in electrochemistry, the scenario that's often used is you got like a container of an aqueous solution, okay? So this is our aqueous solution. Okay, and inside of that aqueous solution, we have an ionic compound in there. Okay, so let's say, for example, we got silver nitrate. Okay, so we got a solution of AgNO3. Okay, and so we know that when we have an ionic compound in water, it's going to want to dissolve, right? And you got these free ions floating around. Whee! They're just swimming. Okay. So far, so good? Okay, now we talked about how a metal has a specific potential, right? So silver has the potential to become, or silver ion, aqueous, has the potential to turn into solid silver, right? And that equation has a certain potential to happen. I don't know what the number is. Okay, but it has a certain number. Make sense? So silver this ionic silver has the potential to become solid silver, and the potential is based on the potential value. Okay, but what happens is we stick a piece of metal inside of this ionic solution. Okay, so this is my piece of metal. Okay, so let's say for the sake of argument, this is solid zinc. Okay. Wow, look at this. Look at that cross-hatching. I learned that in art class. That's what it's called, right? Cross-hatching. Whatever. Anyway, so we add a piece of solid zinc. Now zinc, we know that zinc also has the potential to become aqueous, right? So solid zinc can become aqueous. 2 plus and 2 electrons. And there's a potential for that too. Okay, and so this scenario is significant because what can happen is when you put a piece of solid metal, it has the potential to go into the solution and become aqueous, right? But what the thing is, these metal ions inside the solution can also react with the solid metal and become a solid. And so basically the question becomes, and the scenario that's often posed is, will the ionic metal become a solid? Okay, because when you stick a piece of metal inside a ionic solution, it's going to start providing, it has the potential to give electrons, right? And if the silver ions gain electrons, they can become solid. So what happens is, if this reaction happens, you're going to start seeing a coating of the aqueous metal on top of the solid metal. You're going to start to see the aqueous metal start to form a precipitate around or on top of the solid metal. It's basically going to steal electrons from the piece of metal, and then it's going to form a solid precipitate. And as that happens, the metal here is going to form aqueous metal. So it's going to kind of switch places. One of them is going to solidify, one of them is going to become aqueous. Does that make sense? And so the big question in electrochemistry is, will this happen? Okay, and that's going to be based on their reduction potentials. Now, what did we say about the reduction potential? What makes it more likely for the reaction to happen? Yeah, whichever one's bigger, right? And so basically, if this number is bigger, the potential for aqueous to become solid, if this number right here is bigger than this one, it's going to happen. Okay, so let me give it some numbers. We'll call it E1 versus E2. If E1 is bigger than E2, that means it will solidify. The answer basically becomes yes. But if E1 is smaller than E2, the answer is going to be no. Okay. So that's basically the scenario. If I stick a piece of metal inside a solution with aqueous metal, am I going to be able to leach out the aqueous metal from that solution? Okay. All right. Does the scenario make sense? Okay. Guys, yeah. Yes, you can use this for stainless steel. Basically, will something rust inside of a solution? That could work as well. That's another way to think about it. Okay, let us move on. Let's try a problem. Okay, so you have a solution right here, or you have a problem right here. Okay, and I'm gonna kind of go through, let's draw a picture together just to see what's going on. I'll do it very quickly this time. I won't put into as much work as my masterpiece earlier, but we have a solution. Okay, and if you look at the reactant side, which metal was in the solution?
Silver.
Yeah, silver. So basically the same scenario we had earlier, right? We have silver metal in there. And then what we're doing is we're sticking in a piece of solid zinc. Okay, so exact same scenario that we had earlier. Okay. Now, if you guys take a look at the half reactions, the oxidation half reaction is solid, right? Solid going to aqueous, and the reduction is aqueous becoming a solid, right? So basically, it's the same question I was asking earlier. If I stick a piece of zinc metal in this solution of aqueous silver, will it produce solid silver? Okay, so that's part A. So I'm going to give you guys about a minute to try to think about that, and I want you to write an explanation as well. And if you guys feel comfortable, you guys can do part B, okay, which is basically the opposite. If you put a piece of solid silver in a solution containing zinc ions, will it produce solid zinc? Okay, so take about 2 minutes. You guys can try that out. Make sure you guys write your justifications, and then after that, we'll go over it. All right, guys, let's go over this. So, will placing solid zinc in a solution produce in a solution with silver ions produce solid silver? Okay, so let's do a quick poll. Who thinks yes, it will produce solid silver? Okay, that is everybody, you guys. Okay, I'm not even gonna ask the other one. Yeah, it's true. So the answer to part A is yes. Okay, it will produce solid silver. Okay, so will produce solid silver. Okay. And the reasoning is very simple. If you take a look at the potentials, going from aqueous to solid silver has a greater potential than the other way, or sorry, than if we are going from, I just lost my train of thought. It has a greater potential, sorry, than if we went from solid zinc to aqueous. And so since this is more likely to happen, so you can just write has greater potential. Dang, I can't even write. Okay. Okay, so something like that, probably more better articulated than me, but that's going to be the answer to A. Okay, but if we look at the reverse reaction, if we had solid silver, okay, and if we had aqueous zinc, okay, it's not going to work out that way. And the reason why is because if we flip this reaction, it's going to be aqueous zinc going to solid zinc. It's going to have a smaller value than the other way around. And so the answer to B will be no, and basically the same reasoning. You just need to look at the potentials. Okay. Yes. Yeah, you would also have to switch that. No, so but the quantity, the magnitude of the value. Yeah, did I not mention that? Oh, sorry. It's the magnitude of the value. It's not the positive negative. Yeah, sorry about that, guys. Oopsies. That's pretty important. Huh? So yeah, you got to look at the magnitude of the value. So basically the point is, if you put solid zinc inside silver ion solution, yes, it will produce solid silver. But if you do it the other way around, zinc will not be able to take electrons from the silver. Okay. So if you kind of want to look at this reaction, you can just think of it like this. Silver can take electrons from zinc, but zinc won't be able to take electrons from silver. Okay. Regardless of whether it's solid, regardless of whether it's aqueous. You gotta look at the magnitude of the value. I'm sorry about that, guys, if I didn't mention it. All right, let's take a quick 5-minute break. And then after that, dude, I think we might be able to finish this unit. Yeah, so let's take a quick 5-minute break and then we'll come back together and then we'll finish up the unit. Okay, so we're gonna go through this pretty quickly. Now this looks really complicated, galvanic cells, but also called voltaic cells. Basically what it does is it uses a favored redox reaction. So remember we said earlier about how the potentials allow us to tell if the electrons will be leached from the aqueous one or not, or from the solid one or not. Basically, these cells use favorable redox reactions to move a current. So if you guys take a look here, the side with the zinc, right? Is going to want to take the electrons from the aqueous. You guys see this? And so we're going to look at this. And so if you guys notice, we have a greater potential here. And so what's going to happen is the solid zinc is going to want to give up the electrons to form aqueous. And so what's going to happen then is, as one side, the anode is the side that's being oxidized. As it's being oxidized, there's going to be a current that's formed to the side that's being reduced, the cathode. Basically, what you need to remember is that one side is the anode side gets oxidized, the cathode side gets reduced. So basically, all you need to figure out is which side is being oxidized and which side is being reduced. And from there, you can just write anode or cathode. That's the first important thing, okay? So I'd say if we wanted to kind of write a list of things we want to figure out, is that we want to find the side that's being oxidized. The side that's being oxidized, we can just call the anode. And the side that's being reduced is called the cathode. You guys might know this from electricity a bit more commonly as the negative side and the positive side. Yes, batteries. Okay, and then the electrons move from the anode to the cathode. Okay. Oh my gosh, it all comes together. Yeah, sometimes these people that make names, I think they just do it for fun. Okay.
Wait, is that why, like, if you have that, like, light and then you have that steady thing in the water and it starts lighting up?
What? Spinning thing in the water, what are you talking about? Okay, but anyways, that's the first thing you want to find. And then I guess the second thing would be to find the flow of the electrons. Okay, and the flow of the electrons is basically from the anode to the cathode. Okay. Okay, so one thing I do want to mention is this little thing in the middle. It's called a salt bridge. Jot that down somewhere in your notes. But the salt bridge just makes it so that the two cells that they stay neutral. Okay, because what's going to happen is eventually all the electrons are going to move to one side, and then if all the electrons are just on one side, there's no current. Okay, and so this just helps maintain electrical neutrality. So it's going to keeps neutral. So because there's oxidation going on here, this side becomes negative. Because there is reduction going on here, this side is going to become positive. And then basically it just functions as a battery. So you can actually, there's actually things called wet batteries, and that's where you have two solutions like this and you can produce a current and use it as a battery. Pretty interesting. Yes.
Constantly going back and forth.
So yes and no, because the problem is also the efficacy of the materials that you're using as your wiring, because yeah, if they break down and degrade over time, as the reaction goes on, the anode and cathode will also degrade. There's a scene in Breaking Bad actually where they create these half cells. Do you guys watch Breaking Bad? Never mind that. Never mind that. Moving on. I'm old. Okay, so that's what a galvanic cell is. And this does tend to pop up in the AP test, just to see if you guys can recognize which side is oxidized, which side is reduced. Just remember, anode is oxidation, cathode is reduction. and then they might make you do some math with it. But it's nothing different. Once you figure this out, it's basically the same thing as what we did earlier with the potentials, okay? All right, and then last but not least, electrolytic cells. I'm gonna zoom back in. Okay, so we said that there's a favorability in these half reactions, right? There's one that wants to happen. Okay, in an electrolytic cell, basically what we do is we use outside voltage to force an unfavored redox reaction. So remember how we said earlier, one reaction is favored, right? Whatever has the higher magnitude for the potential. What we can do is we can use electricity, we can use electron movement from the outside, from an outside force to force the one that doesn't want to happen, okay? Good example right here is nickel 2 chloride. If you take a look at nickel 2 chloride, this half reaction does not want to happen, okay? But what we can do is we can use external force to push that along. The key thing, and this isn't very common, so don't spend too much time on this part, is to just remember that we use outside forces to force a unfavored chemical reaction, okay? And this is all just more examples if you guys want to check it out, but it doesn't really matter, okay? Just to let you know, AP Chem is all about focusing on what's important, and this is not that important. If you want to read more about it, it is in your reading. But I'm not going to spend too much time on it here. And then electroplating, I'm also not going to really go over. There's a summary here, but it's also in your book. And then you guys can try a practice problem on your own, but I'm not going to spend too much time on this. A lot of it is just using this equation right here. So make sure you check it out in your textbook, how to use this equation. But it's very simple. I is current, usually given to you. Charge coulombs. That's going to be a constant that you can find, and then you just use time. Okay. That's pretty much it for unit 14. So congratulations, guys. You have finished everything, all the content for unit 14. So you guys should be proud of yourselves. A lot of material. But from here, we're just going to be basically reviewing until the AP test on May 2nd. Okay. Congratulations, guys.